Welcome! In this lesson, we will design a feedback controller for prefetch throttling using last-level cache, misses per thousand instructions, as the signal. Our goal is simple: drive the measured misses per thousand instructions to a target of 4. We will derive a control law and compute the steady-state behavior when each one-step change in prefetch degree changes last-level cache misses per thousand instructions by about 0.7. First, intuition. Increasing prefetch aggressiveness usually reduces last-level cache misses, up to a point. We will model this locally as a simple linear relationship. The output, that is the measured misses per thousand instructions, equals an intercept minus sensitivity times the prefetch degree. Here sensitivity is 0.7 misses per thousand instructions per degree step. That means each one-step increase in degree reduces misses by about 0.7. This is a local model around the current operating point, and it is good enough for a simple controller derivation. Now, the feedback idea. We compare the measured misses to a target of 4 and compute an error. Positive error means too many misses, so we should increase prefetching to reduce misses. Negative error means too few misses, so we should back off the prefetching. Let's draw a simple block diagram to keep the logic straight. Let's derive a simple control law. Define the error E sub k equals y sub k minus y target. If the linear sensitivity is 0.7 misses per degree, then 1 degree step changes y by about minus 0.7. So a natural proportional update is delta U sub k equals error divided by 0.7. Because the degree must be an integer, we round to the nearest integer step. Finally, we update the degree with U sub k plus 1 equals U sub k plus delta U sub k. This drives the next measured misses close to the target in one or a few steps. What happens at steady state with rounding? If the absolute error is less than 0.35, then the rounded delta U is 0, and the controller holds the degree constant. Therefore, the steady state error magnitude is at most 0.35 misses per thousand instructions. That means the steady state misses lie between 3.65 and 4.35, centered around the target of 4. If the plant intercept allows an integer degree to land exactly on target, the error is driven to exactly 0. Otherwise, rounding leaves a bounded residual error within plus or minus half a step worth of misses. Let's run a quick numeric example. Run A. Suppose the current degree is 2 and the measured misses are 6.1. The error is plus 2.1. Divide by 0.7, we get exactly 3. So we increase degree by 3 steps to 5. The next measurement is 6.1 minus 3 times 0.7, which equals 4.0. We have hit the target exactly, and the controller holds the degree steady. Now run B to see the rounding band. Suppose the current degree is 0 and the measured misses are 5.0. The error is plus 1.0. Divide by 0.7 and round gives plus 1. Degree becomes 1. The next measurement is 5.0 minus 0.7 equals 4.3. The error is plus 0.3, which is within plus or minus 0.35. So the controller does not change the degree further. We settle at 4.3, inside the steady state band. 2 practical notes. First, we should clamp the degree to a valid range like 0 through maximum. Second, we can optionally limit the maximum change per update to avoid sudden jumps. Finally, our sign convention assumed that increasing prefetching reduces misses. If your system shows the opposite locally, just flip the sign in the controller. Summary. We modeled last-level cache misses per thousand instructions as a linear function of prefetch degree, with local sensitivity 0.7 per step. A simple integral, like control, delta U equals round of error divided by 0.7, updates the degree to drive the error down. With rounding, the steady-state error is bounded by plus or minus 0.35, so the steady-state misses land in the range 3.65 to 4.35 around the target of 4. This controller is simple, robust, and implementable in hardware or firmware with just integer arithmetic.